I would like to show a work made by Giuseppe De Giacomo, Fabio Patrizio, and me. It's about a composition of partially observable services exploiting their behavior. It's a work related to, I guess that there are some similarity with just shown work by Pier Giorgio. So let's start with a simple definition of what is a service. A service can be considered as a self-describing reactive component, so like a robot or a computational element, Java code, something like that. We can describe the behavior of a service as a transition system that mathematically is a tuple made up by a finite set of actions, a finite set of state, an initial state, and a set of final state, and a transition relation. And graphically, we can represent it like this figure. And notice that even if we have finite state, the behavior of a transition of a service is potentially infinite. So we have loops and infinite computations. The service composition we address is the following. Given a virtual target service and a community of concrete available service, the service composition problem consists in synthesizing a new process that we call the orchestrator that delegates the target requested action to available services in order to simulate the target service. So, in other words, from one side we have a community of a set of concrete available services, so an implementation of these services and also a representation with transition system. And to the other side we have a target service that we want to synthesize. So we have only the specification, so the mathematical representation. So here there is an example. Consider that we have already synthesized an orchestrator. The task of the orchestrator is the following. So the target asks the orchestrator to perform some action, in this case action A. The orchestrator observes the actual, the current state of the community, in particular of the service 1, and know that he can perform action A, and then delegates this action to the service 1. As a consequence, the target and the service that have performed that action change its status, their status, and so the target can ask for another action to be performed, in this case action B, and the orchestrator knows that service 2 can perform action B, and then it delegates that action, and again can the target change its status, and also service 2, but is stateful. And the orchestrator knows that service 1 can perform action C, and notice also that this action was non-deterministic, so the service 1 is now in the state 1, and the orchestrator can observe that it is in this state. And then delegate action C to the services. Oops. Okay. And then we can simulate the target forever. This is the simulation relation. It is a mathematical relation on which all the composition is based on. And it is a relation between the state of the target and state of the community. The state of the community is a tuple in which there is the state in which all the services of the community actually is. And if a couple state of the target, state of the community belong to the relation, this means that for every possible transition that the target could ask, so for every possible action the target could ask, there is an index that represents a service that can perform that action requested by the target. And the target, and for the new state in which the community reached by performing action A, it's again in this simulation. So let's consider that this simulation, it's for each there exists and there exists. It is a co-inductive definition. It has no base case. And so it is easy to understand that if we have that the initial state of the target and the initial state of the community belongs to this simulation relation, then this means that for every possible request that the target service will do, there will be always an available service that can perform that action, and so by remaining in simulation. Once we have computed the simulation relation, extract an orchestrator is an easy task. In fact, we can obtain all possible orchestration by the simulation relation. In fact, we can extract a table like that that relates the state of the community and an action requested to a set of services that represents the services that can perform the action A being in this state. So an orchestrator is a function that, given as input an history of the community, so a state, an action, and then the new state, and an action requested by the target, returns an index that represents the service that can perform that action. So we have already a technique to compose to the service composition in the case in which services belonging to the community are fully observable. But now we introduce the partially observable transition system. That is similar to the previous one, with the exception that it has an observability function that relates from each state an observability value. So in this example, we represent with these dotted lines the fact that these two states have the same observability value. So from the outside, they are indistinguishable. This partial observable transition system is a generalization of the previous transition system. In fact, if this function is injective, the partial observable transition system is actually a fully observable one. So how to here we show some problems that comes out when we have a partial observable transition system in the community. When target asks to action A to be performed, the orchestrator knows that initially all the community transition system are in their initial state, but after he delegates action A, since all these two states have the same observability value, the orchestrator cannot know in which state this service one actually is. So we define a partial observable orchestrator that would be the results of the synthesis that takes as input this time an observable history. So an history made up by observation, action, and then another observation. And from each observable history could be associated a lot of real evolution of the community. So we would like to synthesize a table like the previous one, but with this, the observation, the observed history here. So our idea is to work with knowledge and belief states, so transform all the community services, partially observable services, in fully observable one. This is a known technique for conformant planning with partial observability, but it's in general sound and complete, but in some cases, in particular when we have partial observability with unbounded plans, it is incomplete, and this is demonstrated in this paper by Sardina, Giacomo, Esperanza, Levesque, and KR06. Proofs are based on a reachability problem. Here we have unbounded plans because we have unbounded execution of the target and the community services, but ours is a maintenance problem, not a reachability one. So let's see how this transformation works. Essentially, for each non-deterministic transition that leads this transition system in 2 or more states that have the same observability value, we have to generate a new knowledge state. And all the transitions that can be performed in this state are only those that are possible in all of the original state that belongs to this macro state, and this is a septic approach. In fact, we can notice that here we cannot do any transition because transition B can be performed only in S1 but not in S0, and the same happens for transition A. Obviously, there could be an exponential blow up in certain cases. This is the worst case. And so we generate the whole power set of the initial set of states. Actually, the power set for the exception to the empty state that is not generated, but it's exponential anyhow. But we have some theoretical results. So suppose that we have the original partial observable community and we transform it with the algorithm that just shown all the partial observable service in fully observable one. So we have these two related community. We proved that if we, since the knowledge state community is a fully observable one, we can exploit the standard technique for computing a composition, for synthesize a composition. So if we synthesize a composition and so an orchestrator in the knowledge state community, we have proved that this is also an orchestrator for the corresponding partial observable community. And this is a soundness property of the transformation. And we have proved that also the vice versa holds. So if we compose in somehow an observable composition, this is also an observable orchestrator. This is also an orchestrator for the transformed knowledge state community. The demonstration proofs are based on the bijective correspondence between the history, the observed history, and the knowledge state history. So our theoretical result assures us that we can transform all the partial observable services in fully observable one, make the composition, synthesize a composition in a fully observable knowledge community, and then if a solution exists, this is also a solution for the original problem. And if not, the original problem does not have any solution. So in our maintenance problem, we have proved that working with knowledge states preserves soundness and completeness. So a naive approach is to get as input an XML description of the community and the target, transform all the partial observable services in fully observable one by introducing here an exponential cost. And then encode this, and we specialize game structure, and we use model checking for verification, for synthesis, for this synthesis problem. So we use TLV. And then encode this problem as a game structure and give it as input to TLV. But this approach is computationally challenging because we have to introduce explicitly an a priori exponential blow-up here. For example, a Java program that makes this transformation. We try to optimize this approach by providing a polynomial description to encode a knowledge transition system in TLV without explicitly generating it. So we have an encoding that allows us to delegate all the construction, so the exponential cost to TLV that use the ordinary Barry decision diagrams and symbolic state manipulation, so it is optimized. This polynomial encoding is based on the ideas that in which for each step of the synthesis is not necessary to store the whole knowledge state transition system, but the only relevant information are if the actual state in which the target the system is, that the transition system is final, and which are the actions that the knowledge transition system can perform. So, quickly recap. We have provided an algorithm to transform a partial observable services in a fully observable one by using knowledge state transition system, knowledge state approach. And we have provided some theorems that answer us that we can exploit the standard synthesis technique in order to synthesize the composition. And then a more practical results that is this polynomial encoding that optimize all the synthesis process. Future work is to use, to exploit this technique in a smart environment, the European project SM4all. Thank you. Yes.
Are the same as the action in
yes, but it's okay. Go on.
So
no, yeah, but it's
two questions. What makes a significant difference with the work that we have seen in the previous presentation? So the question is this realistic? Because if you have a really realistic, you should have a requirement, not the same action.
Yes, but it's trivial that if we have some action in the target that and there are no service that perform that action, obviously the composition is not realizable.
No, but I'm just arguing against the fact that whether you should specify exactly the same action that are in the components, because in this case, for instance, you go compare with the previous work, you don't need any planning at all. It is true aware of the assumption, right?
So this is the core problem. Okay, on the core problem you can have the same actions. Now when you apply, you can in fact generate a relation of compatible actions. This is something very simple. Okay, something very simple because somebody by hands writes the relation. Or you can use some technique to derive this relation. But this has nothing to do with the synthesis itself. Okay, so this is really the work on the synthesis. The work on the synthesis, we assume the same action. Okay, or compatible action. You can read it compatible action.
Any other questions? Do we have any questions? I'll ask a question. So
okay.
I'm going to ask something similar to what Carmel asked the last speaker, which is what's your opinion on synthesizing your composition before actually executing it versus doing some sort of an interleaved online synthesis that's predicated on making the observations rather than suffering the exponential blow up of coming to it?
And the problem is, we make an offline planning, let's say, and this has some advantages. For example, that we can have all possible orchestration after we have done the synthesis. So if some services goes down for a certain reason, we can switch to another plan without replanning all the problems. So this offline approach has some advantages.
Can I also complement you? So in fact, this approach generates all the possible composition. Okay, so it's all the plans. Okay, and now when you execute it, you have to choose one of them. Okay? And you don't have to choose until enough time. Okay, so you have all of them. And these are all the possible plans that you can do. And at that time, you can choose reactively or information you can contact.
excellent one where you understand the basic possibilities a priori. So I think we'll thank the speaker.
Okay.